So hello everyone, this is lecture 79 for the mathematical physics. In the last lecture we have completed the Laplace transform, the Fourier transform, and today we'll start Green's function. So in Green's function what we do is solve the differential equations. So you must know about the differential equations. You can see my complete playlist on the differential equations. You must know about it. So what we do here, normally we have homogeneous terms in the differential equation so we can solve them easily. But sometimes it happens that in a differential equation we have a inhomogeneous terms and we call that a source term. And now there is this Green's method and we call it Green's function. That is a very easy method to solve that differential equation which include the inhomogeneous term. And it can be vary, means it can change from one to another, the inhomogeneous term, and we can just directly very easily write the solution after that also. So let me tell you, Green's function method enables us to solve differential equation containing inhomogeneous term, that is we call source term, that is related to an integral operator containing source term. So let we have some differential equation. This is our differential equation, this, only this, see this. And this is given by when we operate some operator on the y, then we get this differential equation. Now if you put this term equal to 0, then that will be a homogeneous equation. But there is this fx term which is inhomogeneous and we call it source term. Now if you can find a method that means that's how, if you find a method that if you change this fx to some other function and you can directly write the solution for that also. So that is what the Green's function do. Means if you change this fx some other function, then just write it here, yx will be, means then the solution of the differential equation will be a to b, means this is defined for some limit, means there are some boundary a to b, then a to b gxt, that is the Green's function which you will find that what is that, and then this source term ft dt. So you will just integrate this and you will get your solution for this change function, means change it to any ft, then this will be your solution. So let's see how can we do that. Now this solution which is, this must to be satisfied in the range a to b, means this is a to b, this is whatever solution we will get, this must be satisfied in the range a to b, subject to homogeneous boundary condition at x equal to a and x equal to b. So there is some line, means this is, we are defining this only in the one dimension, that is in the variable x, and the function is fx, that we call y also. So if it is x is going from a to b and there are some function ft inside this, so this yx can be written in this form for different ft. Okay, so this whatever solution we'll get from here, this must be satisfied in the range a to b and the solution must be homogeneous, means homogeneous boundary condition, these boundary conditions must satisfy, means at a and b this function must satisfy the condition. That is the point here, means the next function, the differential equation we will get, that must satisfy these. So see here that this fx can be anything, means this x can vary from a to b and a to b, then this t lying inside can be anything. So that's why we have defined this yx as gxt ft dt. So for different ft you will get a different yx solution and that can be written directly. Now we will see this Green's function. How can you find this? So Green's function must satisfy this equation, that if you put in place of y the gxt in this complete equation, then that must be, means gxt will give you Dirac delta function x minus t. So this must satisfy. Let's see why. Because only this condition will satisfy, then only we'll get operating g on everyone, will get here fx. How? So if here is in place of y we have gxt, then this solution here it will be, in place of lgxt we will write delta x minus t ft dt. In place of this we are writing this. Now see, this integral is defined only for x equal to means t equal to x, so this will be fx, and the integral of Dirac delta function is 1, so this will be equal to fx, this equal to fx only when this equal to Dirac delta function x minus t. So to satisfy this condition, that's why this Green's function must satisfy this condition. Okay, so must remember these are some properties which must satisfy, otherwise we can't get our Green's function. So let's say we have this where this x can vary from a to b and there are some point t inside this, and this is t minus epsilon and t plus epsilon. So we have this limit for t, and let's solve this limit for, means now we'll solve this differential. In place of y just write the g and then integrate this from minus t, means t minus epsilon to t plus epsilon. We'll integrate this complete equation. Let's see what we'll get. So in place of y we are writing g, so and integrating So it is d by dx px d by dx gxt. So here in place of y we have g, and integrating dx, again in place of y we will write gxt t minus epsilon t plus epsilon. Sorry, here we are writing again this. Now in the right hand side, now this fx is nothing but gxt, and lgxt we defined already. This L is nothing but just representing that we are writing this equation in the y or g. So we are writing in g, so that's why this fx will be drag delta x minus t. So drag delta x minus t and t minus epsilon t plus epsilon dx. Now see, this is differentiation and integration together. So this will give you again the same value px d by dx gxt, and limit will be t minus epsilon t plus epsilon plus. Now this is qx gx dx, write it as it is. Now this is a drag delta function, and integral will always give you 1, because this t is lying inside, means x equal to t. Equal to means this will be defined only x equal to, and t is lying between this, so it will be equal to 1. This integral will be 1, so it is 1. Now see, this g we already said that this is a drag delta function. So if we say that gxt is a continuous function, then this must be value of gxt must be 0 in this limit. And see, if this is continuous, then, and we say that d by dx of gxt is also continuous, then this must be 0, this must be 0, then this condition won't satisfy ever. This won't be equal to 1. So we need to say, if we are assuming this as continuous, then this d by dx of gxt must be discontinuous. Only then this condition can be satisfied. So gxt is continuous at x equal to t, then d by dx of gxt is discontinuous at x equal to t. So these are the properties you must remember for the Green's function. And gxt is symmetric about x equal to t, means at point t, the gxt will be equal to gtx. So whatever x or t you will put, they will equal to each other. And now these are the property you must remember. So let's see what happens to this equation now. This will be 0 because this is continuous. Now this is equal to 1, so put the limits. First this t plus epsilon, then t minus epsilon. So limit epsilon tends to 0, and d by dx of gxt, and limit will be x equal to t plus epsilon, means we just integrate this. So first we will put this limit minus, and see this, after you solve this, it will become pt, means when you put this t plus epsilon in this complete equation, this x will replaced by t, and here also, means when you put this second limit, then again px will turn to pt. So pt can be taken common, so this pt will go into the right hand side, 1 upon pt, and this term is already 0. So in this place we will get gxt and xt plus epsilon minus this same thing, and the limit is t minus epsilon, this equal to 1 upon pt. So you will get this equation. Now we need to find the solution, means to find the Green's function, how can we find? So first, see, you have this equation, and by putting fx equal to 0, you can solve this differential equation that is homogeneous. And let's say we have the different solution, that is y1x and y2x. So these two solutions will be putting here. So gxt can be written as y1x h1t, because this is function of x and t. So let's write it as y1x and h1t, where y1x we find it from the homogeneous equation. The solution of the ly equal to 0, means put ly equal to 0, means this complete equal to 0. Then your solution get, that will be your y1x, and that must satisfy the boundary condition as x equal to a, means you are taking the function between a to t, means you are defining it here. So first we will taking for a to t, then we will take from t to p. So first a to t you will get only y1x, and for t to p you will get y2x. So let's see how can we write Green's function, that is y1x h1t, and it must satisfy x equal to a, because this is including this. And now for x less than b and greater than t, gxt will be y2x, second solution from the this ly equal to 0 and h2t. So y2x is the solution of ly equal to 0, and it satisfies boundary condition at x equal to b. Now it is here, so it must satisfy the condition at b. Now by the symmetric property, gxt must be equal to gtx. So this can be equal only when, let's multiply this with the, means let's write h2 equal to ay1, h2 as ay1 and h1 as ay2. Then you will get ay1 y2 and ay2 y1. That means means h2 is ay1. So in place of this, write ay1. So it will be y2t and ay2 y1x. Now see that this h is function of t. That's why if we take h2 as ay1, then it was, this y1 must also be equal to function of t. So h2 will be a y1t and h1 will be a y2t. So in place of this we will write a y2t, and in place of this we will write a y1t. So the gxt will become this a y1x y2t for x greater than or equal to t means a and t, and for t to b it will become a y2x y1t. So this is your Green's function. Now what we need the value of this a. So how can we find this? So we will use this equation, this differential equation we find. Now dy dx of gxt. So for this is for t plus epsilon means it is something greater than t. So greater than t is described here. So it will be a. Now differentiation of this to x will give us a y2 dash x y1t. So it will be, let's take the a common, because in the both terms we will get a common. So a is outside, and this will give us y2 dash x, and when you substitute this limit xt plus epsilon, this will become the function of t. So it will be y2 dash t and y1t minus now this is for the second one, is for t minus epsilon means something less than t. So this is axt means it will be defined here. So it will be y1 dash x y2t, and y1 dash x will turn to t because you will substitute this limit t minus epsilon. This is x at x equal to t minus epsilon, this you need to find. So this will become y1 dash t y2t, and now this whole term is equal to 1 upon pt. Now what you can do, you can just take this whole term into the denominator of this, and pt and multiply this whole term will go to the upside in the numerator and power as -1. So a will be this. Now you have a, and see this inside term can be written as Wronskian, because you know Wronskian y1t y2t and y1 dash t y2 dash t. If you find the determinant, it will be y1t y2 dash t minus y2t y1 dash t, and this is the same thing. So this a can be written in the this form also. You can find this Wronskian, and you can find the a. So in somewhere in the question it is given that Wronskian is this, so you can find the a value. Now you have a and you have g, so you can write the complete solution, that yx is nothing but gxt ft dt. That's what we defined in this first place. So now this a to b will be separated, means divided into two limits, that is a to x and x to b. So yx will be gxt ft dt, and it is just to replace this by a, and a y to x y1t means for a to x. So a little correction here. So it will be like a y1x y2t means this first function will be a to x, and this is not means whatever you are having, it is not means whatever the function of x will be coming outside, and it is limit will be for the t. So it will be a y1x and y2t ft dt, and plus x to b means a to x and x to b. For x to b it will be the second one. So this will be y to x will be outside, and it will be y1t inside. So a y2x y1t ft dt. So that will be your complete solution. Yx will be this. So if you find your Green's function, then you can just substitute it here, and you can find the complete solution of the differential equation for any ft. So let's summarize this complete concept once again. So we have the differential equation. We must write any differential equation in this form first, then we can find this px from there, and that Green's function must satisfy this condition, and then the solution will be given by yx equal to a to b gxt ft dt. For this first you need the gxt. So gxt will be given by a y1x y2t, a y2x y1t. y1 y2 will came from the solution of this equation, means put ly equal to 0 and solve the differential equation. You will get y1 y2, and you will get y2 y1t in place of, so you will get all these terms. Then you need to find the a value. So a can be given by this formula, that is pt. So whatever you will get from here, the px, in place of x write the t, you will get pt. Then in place of y2, whatever you get y2 dash x, so in place of x write t, so you will get y2 dash t y1t minus y1 dash t y2t. So writing here and just taking this minus power, so this will give you a value. When you get the a, you will get your Green's function, and that's how you find your Green's function. So let's take an example. Given differential equation is minus y double dash equal to fx, and initial conditions are given, means boundary conditions are given, not initial conditions. So y0 equal to 0 and y1 equal to 1 0. So it is defining for 0 to 1, and these are your boundary conditions. Then first we will write this in the non form, this one. So we can write this minus y double dash as dy dx of minus 1 dy by dx. This will again give you minus d square y by dx square. So this is equal to fx. Now this is in the this form. So compare this and you will get px equal to -1. So you have px equal to -1. Now to find the y1 y2, what we will do? we will do this, put Ly equal to 0, means put this equal to 0, minus y double dash equal to 0. So d square y by dx square equal to 0, so dy by dx some constant. Now yx will be c1x plus c0. Now use the boundary condition to find the yx. So first for this boundary condition, for the initial one, y0 equal to 0. So at x equal to 0, c0 will be 0. So it will be, means it will be c1x, y1x will be c1x. So we will assume the simplest solution, that is c1 equal to 1. So y1x will be x. Now for the second one, y1 must be 0. So at x equal to 1, this must be 0. So c0 will be minus c1. So in place of this, we will get c1 x minus 1. Now see, again we need to assume the simplest solution. So we'll assume c1 as 1. We already know we assumed here c1 as 1. So here also we'll assume c1 as 1. So x minus 1. Now you can write this in the question. It was given that you can write it 1 minus x also. Because for x equal to 1, you will get 0 here also and here also. So you can write 1 x minus 1 or 1 minus x. Because you will get 0 for x equal to 1 in either case. So we'll assume y2x 1 minus x and y1x is x. Now you have this y1 y2, you need to find y1 dash and y2 dash. So y1 dash will be 1 and y2 dash will be minus 1, and y1 dash t will be, in place of x write t. So whatever there is, this is constant, this will be 1, y2 dash t will be minus 1, and y1 t will be t, and y2 t will be 1 minus t. So you have all these four terms. Now you can write your, and pt equal to minus 1, because we already find px as minus 1. So x equal to t, then it will be pt equal to minus 1. So you have all these terms. So you can find the a value now using this formula. So in place of pt, write minus 1 and substitute all these values from here. So you will get this. Now this t will cancel out, you will get minus plus 1, and this will be 1. So a will be 1. Now what is gx? A y1x y2t. So a is 1 and y1x is x, and y2t is 1 minus t. Second is a y2x y1t. So a is 1, y2x is y2x. Where is y2x? y2x is 1 minus x. So it is 1 minus x, and second term is y1t, and y1t is, so y1t is t. So this will be your Green's function. And for this is for x greater than t less than equal to 1, and x is greater than 0 less than t, and the limits are 0 to 1. So now I hope you understand how to find the Green's function. And first, only this thing you need to understand. Only remember these steps. These are important, that how to find the Green's function for any differential equation. Only this will be asked in the exam. Now let's change this boundary condition. Let's assume it is y1 dash, means y dash 1 equal to 0, and take the same question by changing the boundary condition. So y dash 1 equal to 0. So again yx will be c1x plus c0, and y1x will be same x, but this time this y dash 1 should be 0. Means whatever you have the function in the initial place, that must give you, the differentiation must give you 0. So y2x will assume the simplest solution, that is 1, because y2 dash x will give you 0 again. So this must give you 0 for any constant. So for 1 also it will give you 0. So y2 dash x will be 0. That's why we assume this solution. Now you have y1x, you have y2x. So you can find y1t will be t, and y2x will be 1, means y2t will be 1, and y1 dash will give you 1, and y2 dash will give you 0. So you have all these three, means all the terms. Now you can find the a. So minus 1 0 t, minus 1 1. You just substitute the values in place of this. So you will get the a value, and when you have a, then you can just substitute all these terms in this. So you will get your Green's function. So this is for x0 to t, this will be x, and this will be t to 1. So by just changing the boundary conditions, we see that the solution or the Green's function will change. So that's how the Green's function helps us. Because the boundary condition is different, then Green's function must be different. Because for changing the source term, we must get the different solutions. What we were getting here. So this must be different from this. So that's all for today. In the next lecture, we'll see some more examples of the Green's function. Then it will be more clear to you. Thank you, everyone.